Think about the invisible handshakes required every time you click a button on a modern website. You likely have a front end speaking JavaScript, a back end operating in Python, and a C++ database. These systems run on completely different operating systems and memory models. Translating and sharing complex arrays of data across this divide without crashing the application is the core friction of network engineering. This diagram illustrates how early web systems attempted to handle that translation. They relied on extensible markup language, or XML. Because XML requires every single piece of data to be wrapped in a custom opening and closing tag, the actual information gets buried inside a massive shell of structural text. This extreme text verbosity created bloated file sizes. When systems tried to send thousands of these XML payloads simultaneously, the heavy text swallowed up vital network bandwidth during transit. The receiving servers then faced a massive parsing penalty. They had to load the entire bloated file into memory and run it through complex translation layers just for the privilege of stripping away the tags and reading the underlying data. The early web was drowning in its own data translation overhead. Network engineers urgently needed a lightweight, universally understood text format to keep systems communicating efficiently. JSON, or JavaScript Object Notation, arrived as the direct antidote to that friction. Instead of relying on rigid markup, it completely abandons heavy tags. It structures data in a clean, highly readable layout. And despite JavaScript being right there in the name, JSON is a language-independent text format. It is stored as standard text characters that any modern programming system can parse natively. By trading complex markup for plain, lightweight text, JSON slashed payload sizes and reduced the bandwidth bottlenecks that plagued older networks. Looking at this diagram of a single JSON payload frozen in transit, the physical mechanics of its efficiency become obvious. It starts with the outer curly brackets that encapsulate the entire document. Inside, data is organized using a strict key-value pairing layout. The key acts as the unique identifier, and the value holds the payload. This specific structure makes the data instantly identifiable to human developers reading the code and machine parsers executing it. JSON accommodates exactly 6 supported data types: strings, numbers, booleans, nulls, objects, and arrays. That tight, defined list is all it needs to represent any standard piece of information. Because JSON natively supports arrays and nested objects, developers can embed lists and child records directly inside a parent field, creating deep, multi-layered hierarchies inside a single payload. In a traditional relational database, grouping this much context requires splitting data across rigid rows and columns and relying on heavy table joins. JSON simply groups all related attributes together in one place. This self-contained hierarchical anatomy allows JSON to capture and transport complex real-world data without relying on heavy external schemas to make sense of it. But the deepest architectural advantage of JSON is actually a computer science magic trick. Because it is derived from the standard ECMAScript rules that govern JavaScript, it mirrors how modern code natively thinks. Watch this diagram closely. As the JSON text string arrives at the backend, its key value structure aligns with the object-oriented memory models used by modern programming languages. It arrives and immediately snaps into native object shapes in the server's memory. This direct snapping process is called universal language serialization. The system converts the text directly into memory objects, bypassing the need for CPU-heavy translation layers. This alignment drastically minimizes the computational tax of data parsing. By mapping data to the structures code already uses, JSON reduced the memory and CPU overhead that made XML-based systems sluggish. Because of that serialization power, any modern programming language can seamlessly read and write JSON natively. This diagram shows the macro impact: document-oriented NoSQL databases. Platforms like MongoDB take these payloads, storing records natively as BSON, or binary JSON. By leveraging JSON's dynamic, schemaless nature, these databases achieve rapid, agile development and massive horizontal scalability across distributed clusters. JSON provided a universal data bridge by aligning the transport format with the native logic of modern code. Interoperability became a feature of the text itself, rather than a problem for the network to solve.